Okay, so I'm very pleased to introduce our final speaker of this session, Grant Barkley, and he'll be talking about biclosed sets and affine root systems.
Cool. Okay. Yeah. Sounds like this thing is on. Yeah. So I'll be talking about biclosed sets and affine root systems, as you just said. So I imagine, a couple of people might be familiar with affine root systems in the audience, but biclosed sets are probably new to almost everybody. So I'm going to define what that is. And most of my talk will just be trying to get the hang of what these things are, what they look like, why we should care. And then I'll talk about some new results at the end. Okay. So it'll mostly be pictures. There we go. Okay. All right. So to begin, let me define the context for these biclosed sets. So first of all, I should mention that the term biclosed is a very overloaded term. Whenever you have something that is closed, you can define something that is biclosed. It's actually synonymous with the word clopen. So a clopen set is one that's both closed and open. And similarly, we'll talk about how biclosed sets are going to be ones that are both closed and co-closed. And co-closed here really means the same thing as open. It just happens that this is the term that we use in this area. Okay, so what's the context? So first of all, we have some vector space V, and we're going to have some set of vectors in this vector space. So I'm going to call this set phi plus because eventually it'll be the positive roots in a root system. But for now, it can just be a set of vectors. So we're going to look at subsets of phi plus. And being biclosed is a property of a subset of phi plus. So if B is a subset of phi plus, we say it's biclosed if it satisfies the following two properties. So given any alpha, beta, gamma in phi plus, so I'm going to call elements of phi plus roots because eventually this will be a root system. So given any three roots, positive roots, satisfying the following relation. So if gamma is a non-negative combination of alpha and beta, so gamma is in the span of alpha and beta, and the coefficients are positive. So we're asking that they're positive, and they can be non-negative, and it doesn't change anything. Okay, and then the condition that we're asking is, so we have two conditions. So the first one is called the closed condition. If alpha is in B and beta is in B, then we ask that gamma is also in B. So we could say it's like closed under non-negative combinations. And then we also ask that it's co-closed. So this says that if alpha is not in B and beta is not in B, then gamma is not in B. The reason that it's called co-closed is that this is equivalent to the complement of B inside phi plus being closed. Okay, and so it's not super important that we parse this definition exactly because we're going to look at pictures and see examples. So for my first example, let's look at the following set of vectors. So take two linearly independent vectors, alpha and beta, and then their sum. And then that will be my set. This will end up being the A2 positive root system. So we'll talk about that later. Okay, so I've drawn pictorially the setup. We have a vector alpha, we have a vector beta, and then their sum is alpha plus beta right here. Okay, now for my first example of a biclosed set, let's just look at the entire set phi plus. That's a subset of phi plus, and you can check that it satisfies both of these conditions. So phi plus itself is already biclosed. We have a biclosed set. There's an example. Also, the empty set is a biclosed set. If you have any biclosed set, the complement is also going to be biclosed. That usually when we have a co in front of something, that means it's dual. And if we have both the condition and it's dual, then when we dualize, then it will still have that property. Just a random intuition. Okay, so let's look at some examples of sets that aren't biclosed because that'll probably be more intuitive to see what's going on. So here, if I take the set that consists of just alpha and just beta, this is not going to satisfy this first property, the closure property, because alpha and beta are both in my set, but alpha plus beta, which is a non-negative combination, is not in my set. So that violates the first condition. So that set is not biclosed, it's not closed. And then here's an example of a set which is not co-closed. So here we have just the element alpha plus beta. And then we have that the vector alpha is not in our set and the vector beta is not in our set. But then again, we have this non-negative combination of alpha and beta, which is in our set. So that violates this condition. Okay, but these are the only two examples of sets, subsets of phi plus that aren't biclosed. So I can write down all of the biclosed sets right here. So I'm just doing that pictorially. So this is alpha, that's beta, and so on. And so we've got 6 different Biclosed sets, and I've arranged them like this to kind of draw a Hasse diagram using these things so that we can partially order our Biclosed sets by inclusion. They're sets, so we can just consider when one is a subset of the other. If we do that, we get this Hasse diagram right here. And this Hasse diagram might look familiar. So this is this partial order is in fact isomorphic to the weak order on the symmetric group. So on 3 elements. So the weak order on S3. So here I've drawn the weak order, and I'll define this properly later. But for now, I just want to like point out some things. So the way that you can determine whether a permutation is covering another one in weak order, you look at the difference between the 2 permutations. So as I go from 1, 2, 3 to 2, 1, 3, the difference is I've swapped the 1 and the 2. So our cover relations in this partial order are going to be swaps of adjacent elements in the permutation. So here I've swapped the 1 and 2, so that corresponds to that cover relation. And then here I'm swapping the 2 and 3. Here I'm swapping the 1 and 3, and so on. So the cover relations correspond to swapping things. And then the way you determine whether you're going up or down is, am I putting the elements out of order or am I putting them in order? If you're putting them out of order, you're going up. So the most out of order element is 3, 2, 1. So that's the top element of the weak order. Okay. And then of course we have some sort of like completely different logic when we were creating this set. We just kind of built it from the top down. We listed out all the sets that we know satisfy our Biclosed condition. And then we just ordered them by containment. So that's how we got this poset. They turn out to be equivalent. This will be a more general phenomenon. And then I've drawn over here a picture of the braid arrangement. So this is a hyperplane arrangement. And it has a very strong connection to the symmetric group. And the reason I've drawn it is because if you look at the regions of this hyperplane arrangement, there's 6 of them. They kind of line up exactly with the elements of these 2 posets. And this will also be a general phenomenon. And you can even figure out what the ordering is on these regions. If you kind of start at the bottom, as long as you're moving away from the bottom, you're moving up in the ordering. And so you can actually define a poset using regions in a hyperplane arrangement called the poset of regions. But I'm not gonna talk about that, but that's a really helpful perspective for looking at weak order and the sorts of things I'm going to talk about today. Okay, so let me describe, pause on that slide for a second. So this is just a very specific example. I had some set of vectors and I have some group, and the question is, what's the connection between these things? And the answer is root systems. So I'm just going to give like a very brief introduction to root systems. I've written like a complete definition here, but you don't really need to know this. So I will try to summarize what this says. So to begin with, we're going to have some like bilinear form on our vector space. And the reason that we want this bilinear form is it'll let us do orthogonal reflections over certain vectors in our vector space. So this is the formula for doing an orthogonal reflection. If you're like doing Euclidean geometry, this is the usual formula, but I'm not making any restriction on my bilinear form. It doesn't need to be an inner product. So because of that, you might have vectors where this quantity, the alpha paired with alpha, is actually 0. So this thing in the denominator could be 0. So we're just going to disallow that. We're not going to look at any reflections over vectors where this is 0. We're not even going to look at reflections over things unless the pairing of alpha and alpha is positive. So whenever we see a reflection, whenever we see the reflection over a vector, that vector paired with itself should be positive. Okay, so this is some linear map we can define given a vector. And so the root system is going to be just some set of vectors over which we can do these reflections. So that's the condition right here. So we have this condition that they're pairing positively with themselves. And then we also are going to ask that if we take any of those reflections and apply it to our set of vectors, that we get the same set. So if we reflect any vector in our root system over another vector in the root system, we should get another vector in the root system. So it's a very highly symmetric set. And you can do that. If you just ask for that condition, you can look at these, but these can be like very not like poorly behaved. The thing that makes a root system is this last condition. And what this says is if we take any element of our root system and we write it in terms of our basis that we picked earlier, then the coefficients are all either positive, or I guess, sorry, they're all either non-negative or they're all non-positive. Okay, so that means that we can't have like alpha 1 minus alpha 2, because then we have a swap of sign. So all the signs need to be the same when we write it in this basis. Okay, so I'll talk more about, this is the same definition right here. I'll talk some more about it in the example that we were looking at before. So before we were looking at the system, it was originally just alpha 1, alpha 2, and alpha 1 plus alpha 2. So just the top part of this diagram right here. This full picture is the full root system of type A2. And you can see that we've added like the negations of the 3 elements we were looking at before. And because of that third property that we ask for our root system, we know that every element of our root system should either be written with positive coefficients in terms of the alpha 1 and alpha 2, or with negative coefficients. So if we just look at the ones that have positive coefficients, that's going to be our positive root system. So that'll be the set that we were looking at before. We'll call that phi plus. Okay, and then everything else in the root system is just a negation of one of these. Okay, and then how do we get that braid arrangement that we were looking at? We can also extract that from this root system. So when you do this, it's called the Coxeter arrangement of a root system. And what that is it's just you take every vector in your root system and you look at the hyperplane that's orthogonal to it. And I should be careful when I say orthogonal here. I really mean the thing that annihilates it in like the dual vector space. So you shouldn't be thinking about the bilinear form when you're looking at like making these hyperplanes. You should just be kind of working formally with these things. But a nice way of doing this is of drawing these pictures is just to think of the hyperplanes as being orthogonal in the usual sense, like in the Euclidean metric, orthogonal to our original vector. So that's how I've drawn it here. So here I have a vector in my root system, and this line right here is orthogonal to it. So these 3 lines are the entirety of the lines that are orthogonal to our roots. And so this recovers the braid arrangement that we were looking at earlier. But you could do this for any root system. And then lastly, and probably the most important thing that we can get from our root system is a group. So when we were looking at our example earlier, we had the symmetric group on 3 elements. Somehow this was related to our original set of 3 vectors. And the relation is this. So by definition, our root system is something, it consists of vectors over which we can reflect. So we can reflect over every vector in our root system. And so these reflections are just linear maps. We can just take all possible compositions of these linear maps. And this gives us a subgroup of the general linear group on our vector space, which is called the Weil group of our root system. And so this will be really important. And as you might guess, if we do this construction for the A2 root system that we were looking at, we get the symmetric group on 3 elements. So yeah, this is the same definition. It's the Weil group is the subgroup of GLV generated by all our reflections. Okay, and so it turns out we don't need all of the reflections to generate the Weil group. We just need the ones that correspond to our chosen basis that we were looking at earlier. So the alpha 1 through alpha n. And so if we just look at the reflections over those guys, those are called the simple generators. And so the pair consisting of the abstract group W and these generators of W turns out to be something called a Coxeter system, which means it has really nice formal group theoretic properties. And it turns out that these properties are inherently tied to the properties of root systems. But I'm going to try to focus on just root systems because I want to do some pictures and give you some geometry. However, there's you can do this entire, you can look at the story of Biclosed sets and everything just using Coxeter groups. You don't need to involve root systems if you don't want to. It's just a bit, you lose a lot of machinery. Okay, so I mentioned that we had this poset structure on the symmetric group called the weak order. And then I didn't really give a formal definition, but here's a definition that works for any, I almost said any Coxeter groups, any Weil group of a root system, I guess, to not be circular. So given any element of our Weil group, we can define an inversion set of that element. This will be the set of all positive roots which are sent to a negative root by W inverse. So remember, our W is acting via linear transformations, and alpha is a vector. So we can just act via W inverse on our vector. And if it doesn't get sent to a positive root, then it's an inversion of that group element. And it's not really important that we understand this definition. Again, there will be a picture in a second where we look at our specific examples. Okay, but then the weak order, now we can define the weak order on our group. It's the partial order such that two group elements, V and W, we have V less than or equal to W, if and only if the inversion set of V is contained in the inversion set of W. Okay, and so this is well defined because it turns out that the inversion set determines the group element uniquely. So let's look at this in action for our A2 root system with a while group S3. So I mentioned that there is a correspondence between that our group. So first of all, our group should be generated by reflections over our roots. And so I've given the elements of the symmetric group on 3 elements that correspond to each of these roots. It turns out that each reflection is just a transposition in the symmetric group once you do the isomorphism to the usual picture of permutation groups. And I've kind of given a specific choice here. So here, this vector on the left, which was alpha, this corresponds to the transposition 1, 2. So the one that swaps 1 and 2 and fixes 3. And then this one's 1, 3, and this one's 2, 3. Okay, and so how does this relate to the pictures we were looking at before? Well, you'll look at, if you look at the leftmost picture, as we go up along the left-hand side, we're adding 1 root at a time. First, we add 1, 2, then we add 1, 3, where I'm using these names that I have up here. And if I look at the middle, what am I doing as I go up the left side? I'm swapping 1, 2, and I'm swapping 1, 3. So I'm introducing new inversions by doing those swaps. And so somehow these Biclosed sets are encoding these inversions. And it turns out that they're actually exactly the inversion sets. So this is there's a theorem you can say in much greater generality than just this specific example, which has been proven in many different forms throughout the years. The specific version is due to Matthew Dyer, who also introduced most of the modern work on Biclosed sets. And like that definition, he is probably like the foremost person working on this. And it's his program that I'll be talking about later. So if we have any root system phi, finite or infinite, then the inversion sets for elements of its while group are exactly the finite Biclosed sets in that positive root system. If our root system happens to be finite, then it turns out that these finite Biclosed sets are also in bijection with the regions of the Coxeter arrangement. So altogether, this theorem explains why these 3 pictures look the same. But the reason that these 3 pictures look the same is because we can forget about the finite everywhere here because our root system is finite. So it raises the question, what happens when we have an infinite root system? So here's an example, the simplest example of an infinite root system. And so here I give the specific definition in terms of vectors. You basically take like 2 vectors, alpha 1 and alpha 2, and then you translate them by their sum as many times as you like. But you don't really need to know the specific numerics there. You just look at this picture. We have alpha 1, we have alpha 2, and then we kind of have copies of them that are extended in length upwards. And this goes on and on upwards infinitely. And this is called the affine A1 root system. Another name is like A1 tilde, which is just reading out this symbol right here. It's the, I'm not going to get into like how this notation works, but they're basically, if you take a finite root system, you can make it affine. And so that's where this name comes from, which is why it looks weird. Okay. And so what's the while group of this root system? The while group is actually isomorphic to the free product of Z mod 2 with Z mod 2. And so this free product, this copy of Z mod 2 is generated by an element I'll call A, and that copy is generated by an element I'll call B. And these 2 elements are actually just the simple generators. So A is the reflection over this root, and then B is reflection over that root. So what are we going to do with this? Let's look at the same thing, the same picture that we were looking at for type A2. So here I've drawn the weak order in a couple of different ways. So in the middle, we have the weak order as defined on the other page for this while group. So here are the elements of the group. It's a free product of z mod 2 with z mod 2. So all we can do is like take our generators and compose them such that we don't go backwards. So like we get A, AB, AB, A, AB, AB, and so forth. And then similarly on the other side, if we start with B. And so if we draw out the poset for the weak order, we get two chains. We start at the identity and we can go up infinitely on the left and go up infinitely on the right, but they never come back together. And so over here on the left, I've drawn the finite Biclosed sets for this root system. And because of that theorem of Matthew Dyer, these two posets are the same. And so here we have kind of a graphical version of it. And then I've also drawn the Coxeter arrangement. So the Coxeter arrangement, even though it has infinitely many lines, is probably the most similar to what we saw before for type A2. So we just had like basically like a spider web of these lines going through the origin. And we can do a full 360 here. Whereas in the posets we were looking at before, there was a top and here there is not. So I want to do a full comparison. So we've only seen two examples so far, so I figured I'd throw a third one in there. So this middle one is called the B2 root system. It's another two-dimensional root system. And so I've drawn the weak orders for these three root systems. And as you notice, the two finite ones both have this property that their poset looks like a circle or like a polygon, whereas the infinite one doesn't. It doesn't close up. It just goes off in two directions. And I'm going to formalize this property that we're noticing like pictorially as follows. So one way of formalizing this is to say, okay, well, if I take two elements inside the A2 weak order, then they have a least upper bound. So this element at the top is their least upper bound. And then they also have a greatest lower bound. This element at the bottom is their greatest lower bound. And so this poset is a lattice. So is this one. But A2 is not, or sorry, A1 tilde is not. A1 tilde does have greatest lower bounds. So if we take any two elements, we can find a greatest lower bound, but it doesn't have least upper bounds. It doesn't even have upper bounds. If I take something on the left chain and something on the right chain, there's no common upper bound. So what's going on? What's the general statement here? So it turns out, even though these are like really simple pictures and there's really no reason to think about lattices when we're just looking at circles, the lattice property continues to work in higher dimensions, whereas maybe some other things you might want to try to describe these as being fails. So it turns out the weak order on a while group is a lattice if and only if the while group is finite. And it's equivalent to say that the root system itself is finite. So that's a theorem due to Bjorner, Edelman, and Ziegler. And they proved a more general version of that, actually. And then Bjorner later proved that if we looked at any while group, the weak order is always a meet semi-lattice. So that means that there's always greatest lower bounds, even though there's not least upper bounds. So that's a very strong property about like lattices. And so we might ask, is there a way to put a top on this right-hand side naturally? And so if you remember from the previous slide, I had labeled this poset on the right as the finite Biclosed subsets of the A1 tilde root system. And so you might ask, why are we restricting ourselves to the finite Biclosed subsets of the A1 tilde root system? What about the other stuff that we think should probably be there? And so the answer is, if you put in all of the Biclosed sets, we do get a circle. So I'm going to call this poset the extended weak order. And this is the poset of all Biclosed sets under inclusion. So when we look at all Biclosed sets, we get a top half of this circle. So if you look at the stuff that's highlighted in green, that is what we were looking at originally. That's the finite Biclosed sets. And then now we have this other stuff. And now this is a lattice. And even better, it's a complete lattice. So what that means is if we take any collection of elements, then it has a least upper bound. So for instance, if I take this vertical chain of green elements right here, it has this least upper bound, which is this element right here, which the picture is a little bit blurry, but this is like all of the arrows on the left half of the root system. So it's an infinite set, and it's kind of what you get by taking the limit as you add one arrow at a time on the left over and over. And so we get this guy. And you can keep going up. you can get this thing in the top left, which is every element of the root system except for the thing on the far right, which should be alpha 2. So every element except alpha 2. Yeah, and so now this is a lattice. This is great. So how general can we make this? Is extended weak order always a lattice? I've only shown you 2-dimensional pictures. I mean, these are really simple. Maybe it just fails horribly as soon as you go to 3 dimensions. But in fact, nobody's ever found a counterexample. And it's been conjectured for, I think, at least 20 years that extended weak order is always a lattice in any dimension. Oh, whoops. And so one of our goals with this project is to solve this conjecture. I mean, spoiler, we did not solve the conjecture, but we did get some nice special cases. So what is known? So there's this theorem that I mentioned by Bjorner, which tells us the finite biclosed sets form a mute semilattice. That's nice. If we can extend that to all the biclosed sets, then that would actually prove the full theorem. There's like a trick you can do to prove the full theorem if you knew it for all biclosed sets, but we don't. And then there's some other results. So before this one, there's some other results which you can prove really easily, like the rank 2 case. So the 2-dimensional case that I just showed you, you could pretty much prove that by looking at it, that is a lattice. But other than that, there's really no examples that are known until Weizhou Wang about 2 years ago proved that all 3-dimensional affine root systems satisfy this conjecture. And so the only non-trivial examples here are, there's only 3 of them. So they're called A tilde, C tilde, and G tilde. I'm not going to like define these, but there's a nice classification of affine things, and those are the only really non-trivial examples. So Weizhou Wang proved that. Oh, sorry. Here's the definition of an affine root system, which would be helpful. So to kind of skip details, an affine root system is a root system satisfying the special property that there's a non-zero vector whose length under our bilinear form is 0, and this is the unique thing up to rescaling. So there's only one vector that satisfies this property. Up to the rescaling obviously preserves that property. Okay, and then there's a sense in which these affine root systems are the least infinite type of the infinite root system. So if we have an affine root system, it turns out there's an associated finite root system, and we can rebuild the affine root system from that finite root system using this root delta, or sorry, this element delta. So there's like this, the fact that it reduces kind of to the finite case gives you a lot of traction for proving theorems about these and understanding what they look like, that you don't have in the general case. So we were able to use this traction to prove several things about biclosed sets in this case. So one thing, biclosed sets have a nice asymptotic behavior. You can kind of look at the behavior of a biclosed set and infinity. And if you do that, you get a nice geometric description in terms of the faces of the Coxeter arrangement for the finite type thing associated to it. So yeah, there's probably some nice pictures to do, but I am about out of time. So I will hold off on that. So another theorem that we proved is that there's these explicit combinatorial models that you can give for the Weil groups, which we actually have explicit combinatorial models for, which are these 4, A, B, C, and D. And these models for the biclosed sets are stated in terms of orderings of the integers. So somehow we can like look at certain total orders of the integers and extract biclosed sets from those, and vice versa, up to some technicalities. But this gives us a nice way of seeing biclosed sets, because with the definition just as given, it's kind of hard to get your hands on them. And then the last thing is we actually proved Dyer's conjecture for all affine root systems. So this is extending Weizhou Wang's result for the 3-dimensional ones. We proved it for all affine root systems that the extended weak order is a complete lattice. And then despite the fact that I listed this right after these 2 results, that proves actually uniform. It doesn't use any parameterizations that I mentioned right here. So we do actually have some nice like proofs, alternative proofs in these cases. I guess I should just say in types A and C that are very explicit. If you want to look at those, they're in the paper, which is on arXiv. It's called like combinatorial descriptions of biclosed sets. And then I think I'm about out of time probably. Yeah. So I'll skip this slide and thank you.
Thank you. Any questions?
since this is basically Coxeter theoretic, it's independent of the realization of the root system, but I was wondering if there was something special that happens in particular for the A2 even root, using that root system, if something, because that has 3 different root links to it.
Okay, yeah, so it turns out that the constructions all here all only depend on the Coxeter group, as you mentioned. So yeah, nothing in particular happens because you only see the reflections. Essentially, the Biclosed sets only depend on the reflections. That condition forces whenever you have a multiple of a root in a Biclosed set, you actually have all the multiples of that root in there. So yeah, you don't see anything extra when you have non-reduced root systems.
So I have a question. When you look at all your Biclosed sets, it looks like you have basically 3 kinds of things: the finite one, the infinite ones that whose complement is finite, and you kind of reverse your poset and put it on top, and the one whose complements are also infinite in the middle. Is this behavior that generalizes, or is it just because we're on a toy example?
Yeah, that's a great question. So let me see if I can find the picture that has the full. Oh, there it is. Okay. Yeah. So what you're saying is that we have kind of like 3 regimes. We have these finite Biclosed sets. We have these ones on the top whose complement is finite, and then we have these ones in the middle who are both infinite and their complement is infinite. And so the question is, to what extent does this carry on in all affine types? So the answer is, as I just stated it, of course, that's like a trichotomy, so that they all satisfy that property. But you might ask, like, are these ones in the middle, do they satisfy this regularity property that they're both infinite and their complement is infinite? Do they satisfy that for like every way of computing that? And the answer is no. You can actually have a bunch of complicated stuff in the middle. So yeah, this is just a very simple example.
Yeah. I have 2 quick questions. So first of all, for finite case, we know that the closed subsets correspond to Cartan invariant subalgebras in finite case.
Okay.
So here you are using actually by closed you mean real closed, that is closed subsets of real affine root system. I wonder if there is any connection with structure theoretic side there.
It's a good question. So the answer is every regular Cartan subalgebra of a Kac-Moody algebra will give you one of these Biclosed sets. Or sorry, it will give you a closed set. And then if you appropriately check that the complement is also closed, and you'll get a Biclosed set. But not every Biclosed set is the set of real roots of like Cartan invariant subalgebra of a Kac-Moody algebra. If that answers your question.
One more actually.
Okay.
So here you are using mainly weak order, right? So do you want to have any word about higher nullity examples in extended affine root systems? There as well you can define that weak order and these posets.
Sorry, what
higher nullity example? I mean, maybe extended affine, untwisted extended affine Lie algebra setting. Nullity 2, nullity 3. So affine is of nullity 1, right?
Sorry, what is the word you're saying that is 1? Set? Nullity? Nullity. Oh, nullity. Yes, sorry. You can yeah, for any nullity. Sorry, I can't hear today. Yeah, so you can define so we only studied the affine case, but the definitions and the conjectures are still expected to be so the definitions still work for higher nullity for hyperbolic things. And the conjectures are still expected to be true. Like we've checked a lot of things very extensively and have not found any counterexamples. Yeah.
Thank you.
Mm-hmm.
Any other questions?
Go back to the last slide. This?
Yeah.
Just want to look at that. Okay.
Okay, let's thank the speaker one more time.